Okay, so now let's come to quantum key distribution. So in the past few lectures, you guys learned a lot of basic concepts, right, of quantum gate, qubit, all this, but then you haven't had a chance to know, what the quantum, quantum can do for information and computation. And I remember this is similar to what I had for my first computer class. Is that at the time, you don't have Windows, so you have Windows 95, but unfortunately my elementary school doesn't have that. So what they're telling us to do is that, okay, you can type in some command and then you can draw, a triangle or draw a circle. And then at the time I was thinking, but I can draw that with my hand, right? Why would I use a computer? So I think you guys probably may be having the same feeling of quantum computing and quantum information is that, okay, you guys have a lot of definition, but then we never really show you one concrete example that quantum can do something that classical computation or classical information cannot do, right? So the quantum key distribution is probably the most mature quantum technology now that can do something that classical computer or classical information channel cannot do, okay? It's just theoretically classical computer cannot do that. And let me explain a little bit of what key distribution is, right? What is a key? What do you mean by that? So this is the idea in the cryptography, okay? So how you encode information, how you encode. For example, let me put it this way, a very simple one. Like my office, suppose the room number of my office is a secret, okay, which is not 220. That's my office number, and yeah, it's funny is that a lot of times I think about it is that there are many incidents where students actually kill professors. And then that's actually very easy, is because our room number is actually on the website, and then the classroom number is also publicly available. And then, so we actually would think twice before we fail any student, okay? So the room number is 220, okay? And if I don't want people to know that, I can make a very simple code, is that this is my room number, but I encode it as 331. Right? How do we encode it? Is that for each digit I add 1. Right? I add 1, okay, to make 220 to 331. Right? So if an angry student go to 331, okay, try to find me, but then unfortunately he probably will meet Professor Lee, another professor, and then he will take the bullet for me, okay. And so in this case, the key is the function of add 1. Right? Add 1 to each digit in this way is a key. Okay, you get your information, and then you use the key to understand, okay, what process do we need to decode the information to get the real information? Okay, it's 220 in this case. And of course, okay, let me try to go over a little bit of the foundation of cryptography. Is that if I give you the number 331, okay, in theory you can't break it because you don't know the key, right? You don't know the key. And also in theory, if you just know 331, it could actually mean anything, right? Because we can have many different keys. However, using this key is not very safe. It's because if you don't change the key, you use the same key for a lot of information, then eventually people can find out the pattern and then decode your information, okay? For example, the very famous, if you watch the, I think it's a movie about Turing, right? And then he helped Great Britain to break the coding system for the Nazi Germany. And then what they actually used is the first message from from Germany sent out to each troop. It's always about the weather. It's always about what weather it is today, and then people try to the commander try to collect weather information from all different battleground, and they try to make decisions. So they use that piece of information, okay, because and then once you have enough of them, and then you can try to use computer, okay, and to cross correlate them, and then eventually you can find out the key, okay. And in this case, if I encode my office room in this format, and I also encode my classroom information in this format, and also my lab information, then it's very easy to cross them together, and then you find what the key is, right? So a better form of the key is that you can see how the key can be more and more complicated. For example, I can, instead of adding 1, I can say add a number k. Right, add a number k. And the k can be, for example, from 0 to 9, right? It can be 10 numbers. And then all of a sudden your key, okay, breaking this key become 10 times more difficult, right? Because, this piece of information, 220, can be, if I add 5, right, it would be 775. Right, if you don't know and think about it as fitting the parameter in a function. Right now you have 10 variables, so in principle you should know 10 pieces of information, okay, to break it, and 10 pieces of information to break it. So so let me kind of explain, okay, what the modern key actually work is that suppose you have a series of binary information. Any information can be converted to binary. For example, all these letters, you can use binary digit to represent them. Let's say you have information of x, right? So the key, what the key does is you convert x into y, which is equal to f of x, right? A function. And then this function can be very complicated, and then can have a lot of parameters inside. And then so your key, okay, can be, for example, there's parameters x, and then k1, k2, k3, all the way to kn. Okay, all the way to kn. So it's a multivariable function that knowing the information, well, knowing y itself is not good enough to break it. You actually have to know all the keys here, k1, k2, all the way to kn. And and you kind of can see, okay, the possibilities, right? Let's say the k are binary, and then the possibility of the combination of different keys are 2, okay, because it's a binary system, 2 to the nth number of keys, right? Different combinations of 2 to the nth combination. These are all the possible keys. So that, as you guys have learned previously, right? So when n is very large, it's actually almost impossible for anyone trying to break the key. Okay, so classically, if you only have classical computer, in principle this is safe. Okay, that's why we can actually do the banking, all this in the on our cell phone. And then I think some of the I don't know if I can say things like this because like I'm on a foreign visa, so I can't comment on any political things. But I really do think some of the behaviors you guys do on certain Tuesday can be moved to smartphones, and there's ways to encrypt whatever you're doing, okay, on your phone. And I can't say the word out loud because it just takes one person to cancel my visa, and then but we can still do this class because it's online now anyway. So now let's see how the information is transferred in our modern society, right? Suppose you have Alice, and then you have Bob, and then Alice wants to send information to Bob, right? So what you do is that let's say the information is a piece of string called X, right? That's the information he wants to send. She wants to send to Bob. And then what she would do is that she will first send the information Y, right? Y equals to F X K1 all the way to Kn, right? He will send the encoded information from one channel, okay, to Bob. And then usually people will send the key, the K1, K2, Kn, okay, will send it to through a different channel, right? You don't want to have the information and the key in the same channel, okay? Then so this way, okay, let's say someone is doing eavesdropping, and then let's ignore that first. Let's just say, okay, Bob received this piece of information F, and then what he needs to do is that he needs to apply a reverse function, okay, to get back X, Y, and K1, K2, all the way to Kn. Right? He needs to do this reverse function where he received the encoded information and the key, right? And this way he can decode the information. And this actually is nothing fancy, right? So actually a lot of things that you use in the computer are encoded in a way not to provide protect the information, but to increase the efficiency. For example, right now the video, okay, you guys see here, is actually encoded in different format. Zoom actually uses a format, and YouTube uses a different format. And the way that for Zoom to work, you guys have, I don't know if you guys try to share your screen with other people and then play a video. If you try to do that, you will see that the video picture is very laggy. Okay, and why that happened is that the encoding format used by Zoom is that by analyzing the difference between frame, okay, and then because they're assuming that when you're sharing the screen, your screen is not going to change very rapidly, okay. But then when you play a video, the video changes all the time, and then that encoding format is no longer efficient, right? So that's why you share the screen and then play video. Zoom is a terrible format to do that, okay. And so this happens every day. You can use it to compress information, or you can use it to send classified information or protected information from A to B. Now it's very, very obvious, right? This information channel is not 100% protected, right? I can have people eavesdropping here. Let's say, what's the name of it? Eve, yeah, I think I remember that. Eve or Eva, okay. Okay, if she get both channel, the channel of the encoded information and the channel of the key, and then if she's smart enough to figure out this function, okay, the inverse function, then she can actually get all the information as Bob. And at the same time, if she's doing a really good job, for example, classified information can be duplicated, right? So when she collects the information here, she can keep a copy and then send another copy to Bob, so that Bob and Alice will never know, okay, there's someone eavesdropping them, right? So any questions here? Okay, good. So now let's think about what we can gain if we start to use quantum. The situation that we're trying to create is that by using a quantum, the quantum key distribution, that even if the eavesdropping person have access to both channel, okay, she cannot get the information you try to send to Bob. Okay, so let me say that again. Even if have full control of these two channels, she will not have the key Alice sent to Bob. So that in theory, okay, quantum key distribution can be 100% protected, okay, it's 100% safe, unless you have a spy at A and B, okay? Unless you have spy at A and B, which, just read out the result and then do things like that. In that case, nothing is safe, right? So and now let me kind of walk you through of how this could happen. The basic idea of how this will happen actually come from the quantum measurement, right? You guys know that if there's a state, okay, in a superposition of 0 and 1, and if anyone measure that state on the basis of 0 and 1, right, the measurement result will be 0, can only be 0 and 1, right? So your state collapses into 0 or 1, right? Into one of these states. So the measurement itself, the quantum measurement itself, change your quantum state, right? This is a very basic idea. So now you can think about it. If trying to see, okay, what Alice is sent to Bob, right, the result she get will be different from, well, let me put it in a different way. So if doing this measurement, she's changing the state that Alice sent to Bob, right? After she measured it, the state that Bob is supposed to receive will change into either this eigenstate or that eigenstate, right? So Bob is no longer receiving the key that Alice sent to him, right? So this is actually the basic principle of why we can develop something using quantum that can be 100% secure. And then the other thing is that because when you do this measurement, there's no way you can do alpha and beta, with one measurement, okay, without any prior knowledge. So if after the measurement would not be able to reproduce a state like this and send it to Bob, right? So when she measured it, she destroyed the state. Okay, the state collapsed into 0 or 1. So when Bob received it, it's a different state compared with the state sent to Alice. And now let's dig into a little bit details and then and get some background of how to really design a protocol to keep your key distribution safe. And one thing I want to say here is that the key distribution, okay, one thing about the key, if you think about it, is that the key is a piece of information shared by Alice and Bob. Okay, it doesn't necessarily has to be sent from Alice to Bob, right? As long as Alice and Bob has the same key, okay, then Alice can use that key to encode the information and send the information. Okay, so it doesn't necessarily mean that Alice needs to send to Bob or Bob needs to send Alice. It can be co-generated by Alice and Bob using quantum measurement. Okay, now let's look at one of the probably the most useful things to understand, okay, or to kind of think about how to design quantum key distribution. We've talked about this before. Is that previously we say that in most of the system we look at the ground state, excited state, right? We label them as 0 and 1, okay, and then as the basis for your system, right? You can think of it as the base vector x and y in your coordinate. But then we also say that it doesn't have to be this way, right? You guys learned this in the block sphere. For example, right, if this is 0, this is 1, your basis could also be, this is, let's say, minus, this is plus. right? As long as the base vector are perpendicular to each other, and then also they are complete, right? You can describe all the possible state with these two different bases. So let's say the bases plus and minus. And plus and minus are just linear combination of 0 and 1 state. Okay, so 0 and 1 linear combination. And this is actually very easy to achieve in some optic system if you use polarization. As I previously explained, right? So when you have light, for example, propagating perpendicular to the whiteboard, then your polarization of the light, which is the direction of your electrical field, have a degree of freedom. It can be any direction in this 360 degree, right? So you can say that the direction pointing towards the right, when the polarization is pointing towards the right, is 0 state, and pointing upwards is 1. You can also say pointing 45 degree is plus and pointing 45 degree down is minus, right? And then we also say that it's very easy to measure all this is because if your measurement device is polarization sensitive, then you can simply rotate, right, your measurement device by 45 degree to change from the 0 and 1 basis to minus and plus basis, right, if you want to measure at different bases. Okay. Now, let's see, one thing is that, let's say, if I encode information in 0 and 1 basis, right? The information is encoded in 0 and 1 basis, and I encode it in the same way as classical information, right? 0, 1, 1, 0, 1, 0, okay? And then, now let's think about it. If I'm measuring the polarization in plus and minus basis, what will happen? So if your information is encoded in 0 and 1 basis, but then your measurement is done at plus minus basis, what will happen? Any guess? So let's take this as example, right? Suppose this is the ground state, okay? 0 state, while 0 state pointing to the right. And then if I measure this state, using plus and minus basis, what are the possible results? Andrew, try to say something? Yeah, it's actually also equal probability, right? Because the 0 is in the middle between plus and minus, right? So you have 50% chance of measuring, 50% chance of measuring plus, and 50% chance of measuring minus, okay? And then this is the same thing for the 1 state, right? 1 state is here, and then it's just a different minus sign, right? If you put it this way, right? You see that it's also in the middle between plus and minus. So when you're measuring 1 state, okay, it's also 50% plus and 50% minus, okay? And the same thing, if you encode information in plus and minus, say plus and minus, and then you measure it, if you measure it in 0 and 1 state, right? The 0 and 1 basis, then what you will get is 50% plus, sorry, 50% 0, 50% 1, okay? And and this just makes sense, right? If you look at it from a linear perspective, 0 is simply a linear combination between plus and minus. Of course, it's 50-50 equally contributed. And what this tells us is that if you want to extract the information, you have to measure it at the same basis of its encoded basis, right? The measurement basis has to be the same as encoded basis, and this is kind of like a common sense, right? If you encode your classical information in voltage, and then you should measure voltage, you shouldn't measure current, right? So it's a similar things to this, okay? And what quantum does here, the superposition, is that if you use the wrong basis, okay, 45-degree wrong, right? So it's actually, you can see that it's actually completely wrong. If you measure it in the wrong basis, you actually get zero information about the encoded information, right? Because it's, no matter it's 0 or 1, okay, regardless of what information you have, the result is always random, right? The result is always 50% plus, 50% minus. So you extract zero information from this measurement. Okay. Any questions? Okay. Then we can start to talk about the protocol of how to do the quantum key distribution. What I would do is that I would just write down the protocol first, and then you guys can have time to think about it, what it actually does, and then we will explain how it works. Okay, so now the carrier we're going to use to generate this key, quantum key carrier, okay, is single photon. Later I will explain why it's a single photon. Okay, and then you're using the polarization of the photon, right? The polarization of the photon to carry the information. And the direction of this photon is photon from Alice to Bob. Okay, from Alice to Bob. And then the key is actually generated when Bob do some measurement, and we'll explain that later. So the basis or the information, how we prepare the information, how we send out information, is that we send out the information in two different type of bases. The first one is horizontal and then vertical basis. Okay, this is horizontal and vertical. It's like the 0 and 1, okay, in the previous example. And then we also have 45-degree up and 45-degree down. Okay, these two form another basis, which is this. You can use different symbol to represent it, but it's, it's the same thing. It's just polarization of the photon. Okay, and then if we want to send the information 0, okay, we can encode it in the horizontal and vertical basis. 0, okay, the horizontal means 0, and then the up and the 45-degree up also means 0, right? So there are two ways you can send out 0. For the vertical, for 1, okay, you can send out vertical 1, or you can send out a 45-degree down, right? So what we're doing is that it's binary, 0 and 1, but then because it's photon polarization, so you have the freedom to choose your basis. So we choose two types of bases, horizontal and vertical. You can use it to express 0 and 1. 45-degree basis, you can also express 0 and 1. Okay. It's similar like in the classical computer, you can use voltage, or you can use current, or you can use any other things. Okay. Now, it's very important here to know that why it make it safe. Let's say if Alice send out information 0 on horizontal basis, right? Alice sent out H state, but then if, right, Eva is here trying to do if dropping, and then she doesn't know which basis which two of the bases Alice used to encode this information, right? Suppose if choose the correct basis, she measured it with horizontal and vertical basis, then of course she can get the information, right? You measure horizontal state on horizontal basis, you get horizontal, and then you get the same information as Alice sent out. But if if measures on 45-degree basis, right, 45-degree basis, and then as we discussed, when you measure horizontal state on 45-degree basis, you get a random result, right? You get a random 45-degree up or random 45-degree down. So if she chooses the wrong basis, then she gets 0 information, right? It's just a random number, okay? It's just a random number. And this is actually the key, okay, how we can protect it. Now, we can start talk about the protocol. Any questions to this point? Okay. So first step is that Alice generate random number. Random binary number. So it's 1, 0, etc. You might wonder why is it a random number but not a number that that by design, because the fact is that the key, okay, it doesn't have to be a specific thing. It's a piece of information shared by Alice and Bob, right? So what the key is actually doesn't really matter. As long as Alice and Bob have the same key, even if it's generated by a random number, it's still useful, okay? And then let's see if we can put it here. Okay, let's say, I wish I have a larger whiteboard. Okay, let's say, I'm really run out of room. Let's see. Okay, let's try to do it here. Let's say Alice generate random number 0, 1, 1, 0, 1, and keep going. Okay, the random number, this is step 1. And the next step is that Alice randomly select basis for each number. So each number can get a randomly selected basis, right? So the first number have a basis might be different from the second number, right? So you generate a random number for each of these numbers. Okay, you just generate in step 1. And you can kind of see, okay, what we are going here is that if the bases are randomly generated, and then if you don't send out information of what basis you're using, then if there's no way that if can measure the information, right? Because if if she also does the measurement randomly, she can only get 50% of the basis correct, right? So let's say The basis here we have is horizontal basis, 45-degree basis, horizontal basis, and then 45-degree basis, right? And then this randomness is very important, right? So if you have a pattern, right? If like you write down by human, if you have a pattern and then Alice or Eve, right, recognize that pattern, then she actually can try to, then it's actually possible for Eve to actually guess, okay, what are the bases you're using. And so if you ever design this system and then you try to generate random number from MATLAB, you just don't do it because MATLAB is the same for entire around the world. And then as long as you use the same seed, the MATLAB will generate the same random function and random number, and that's not a true random number. A true random number actually has to be generated by a quantum mechanical way. And then people actually sell this, okay, the true random number generator. Okay, and now once you select the basis for each of this number, then you can prepare the photon prepare photons for each number. Okay. For example, if you choose horizontal and vertical state, then the photon you get is in horizontal state, and then this one is in 45-degree up state. 1 second. Yep. 45-degree down state. Okay, this is 1. Okay, and then this is vertical state, horizontal state, and then 45-degree down. Right, so you can prepare this photon. And the next step is that you send all this photon to Bob. Okay, send photons to Bob. I think I can remove this side. We do need more room. Okay. So when you do this, okay, keep in mind that the number, okay, the actual number generated by Alice randomly, and the basis used, okay, also are generated randomly by Alice. This information are not sent to Bob directly. Okay, they are kept in Alice's place, and what's sent is a combination of these two. Okay, when you use the basis to encode this information, you send out a photon. Okay, you send out a photon. You don't tell anyone, okay, what the basis you use or what information it is. Right? You just don't tell people that. Okay, then when Bob received the photon, what does he do? Right? So when Bob received the photon, Bob, okay, also randomly select measurement basis. By random, I mean randomly choose from the horizontal or vertical basis or the 45-degree basis. Right, so this is fairly simple. You can generate a random number. If it's 0, you use this basis. If it's 1, you use the other basis. It's like randomly choose a basis. And then after you randomly choose the basis, you use the basis you choose, okay, to measure the photon. okay, and measure it, and measure photon. Okay, and let's give an example here. For example, the basis Bob select, this is Alice basis, this is Bob's basis. Bob's basis, let's say it's HV, 45 degree, HV, and 45 degree. Right? These are the bases that are randomly generated by Bob, and then he uses bases to measure the photon that Alice sent to him, right? And then now we can kind of see what will be the measurement result. If Alice, right, and Bob are using the same basis, then Bob will be able to know what number Alice encoded, right? So for example, for the first number, because Alice and Bob are using the same basis, so Bob will be able to measure 0. Right? The measurement result will be 0 because you're measuring horizontal photon by using horizontal and vertical basis. So you can detect it's a horizontal photon. But on the second number, you see that the Alice is using 45 degree basis, and then Bob is using horizontal and vertical basis, right? So Bob used horizontal and vertical basis to try to measure a state that's 45 degree pointing downwards, right? And in this case, he actually couldn't get any information, but then just measure a random number, right? It could be 0 or it could be 1. So he has 50% chance of getting the same number as Alice sent out, but then 50% chance of making a mistake, right? And then if you think about it, there's only 0 and 1, so the measurement didn't tell you any further information. It's the same as guessing a number, right? And then we can apply to this here as well, right? They are using different bases, so 0 and 1. Same basis, you get 0. Same basis, you get 1, right? So for the first 5 numbers, 3 of them, you can predict Bob can get the answer correctly. And then there are 2 of them that Bob would just get a random number. Okay, the number is not necessarily the same as Alice sent out. Okay, and then 6 is that after all this measurement, Alice and Bob, okay, after all this measurement, publicly announce their basis. Right? After everything is done, Alice and Bob tell each other and also tell everyone, okay, it doesn't really matter, tell people what basis they're using, and then this way, okay, Alice and Bob would know, right, if they're using the same basis, then the number belonging to that basis is the same, right? For example, in this case, the first number, Alice knows it's 0, Bob knows it's 0, Alice sent out 0, Bob's measurement is 0, but then if they don't know the basis and Bob doesn't know if 0 is really the information or is it just a random number, right? But when they publicly announce their basis, Alice and Bob both know, okay, this number, the 0, is shared by Alice and Bob, right? It's shared by Alice and Bob. And the same apply to the 4th number and the 5th number, right? So this 3 number will know that neglecting all noises or other errors, if the system is perfect, then we know that okay, these 3 numbers, Alice and Bob, share with each other. Okay, share with each other. Then the final step is that Alice and Bob pick out all the numbers that they use the same basis and then use that as a key. Okay, use that as a key. So for example, this one, we just send out 5 numbers, and then three of them we know, well, Alice and Bob know is the same, so that the key here, okay, is 0, 0, 1. Okay, that is a key. That is a key for the quantum key distribution. And then if you look at it, the key is actually not sent from Alice to Bob. It's also not from Bob to Alice. It's actually generated when Bob decided to randomly select the basis and do the measurement. When he does the measurement at that moment, okay, when he selects the basis at that moment, he and Alice, okay, together decide what number here will be used as a key, right? Because if they select the same basis, then that number will stay. If they select different basis, that number will be abandoned, right? So, it's not really an information flow from A to B, but rather it's a code-generated information, okay? Now, let's look at a very simple question: is that why is this? First of all, okay, I think we both understand now that the information, okay, the key can be shared by Alice and Bob, but why is it safe? Why is it secure? Right? Why is it secure? Now let me see if I can. Let me put it down here. Bob. Okay. Now let's say in between Alice and Bob, Eva, okay, is doing the eavesdropping, right? So let's say Eva is really good, and then she has full control of this channel. So whatever photon Bob receives, Alice, okay, can have a look at it first, right? Whether she decided to look at it is a different story, okay? So the photon has to pass through Eva, right? Now let's see, if you're Eva, what would you do? Trying to steal the key, what would you do? So there's actually not a lot you can do, right? Because you don't know the basis Alice is using, right? Because that information is kept at A, right? It's not shared in this channel. So unless you break into A, or the location of A, well, in that case, you don't need to steal this. You can just steal the information if you really can break in, okay? So Eve doesn't know that. So the best Eve can do is probably use the same basis all the time. This is one strategy because that covers 50%. Or you just also use a random basis. That's also 50%. Okay, there's really not a winning strategy here. And let's say if Eve uses, let's say, did I write down an example here? Yes, okay. Let's say, wait. Where's the example? Oh, I didn't give an example. Okay, so let's create an example here. Let's say for the sake of time, right? Let's say Eva is really lazy, and then she just used one basis. That's the horizontal and vertical basis, and that's fine. It's because you will get a 50%. The same basis as Alice. Oh. Right, because Eva doesn't know what Alice has, so she just measured it using the same basis. Okay, and then what will be the measurement result? Right, the measurement result, if they're using the same basis, then that's fine. The measurement result will be 0. And then the photon, okay, after the measurement will still be at the original state, right? Because if you measure an eigenstate, it will not change, right? So, and then for the second number, it's actually measuring at different basis. so that you will get a random number 0 and 1, right? 0 and 1. And depending on 0 or 1, your photon will actually be horizontal if it's 0, or vertical, right? If your measurement result is 1, right? So you change the number now, okay? You change the photon now. And the third one, you're using the same basis so that you have 1 and then vertical. This one, again, you're using the same basis, so you have 0, horizontal. And then this one, you're using different bases, so you will get arbitrary number here. This is not a great example, but either way, okay, let's use it. So horizontal and vertical, right? So either horizontal or vertical. So this column shows you, okay, what's the number, right, get by Eva's measurement. And then this row gives you the photon state after Eva's measurement, right? Because the measurement will change the state, right? If you measure 0 at horizontal and vertical state, then your photon will collapse into the horizontal state, okay? So now let's look at it. If we add Eva here, if we add Eva here, okay, what will happen? What will happen? So the first photon is fine, it's 0, okay, because Eva's eavesdropping doesn't change the state, that's fine. The second one, it's also fine, it's because previously it will already be a random number. Now you just generate a random number at Eva, right? Because Eva and Bob are using the same basis, so it's again a random number, that's fine. And the third one, okay, is fine because Eva doesn't really do anything. He's using the same state as Alice, and the same as Bob, same as fourth photon, right? It's also using the same basis, so that the number are actually shared by 3 of them, okay? And then the fifth photon, okay, is the one that caused a problem. You see, the fifth photon is that Alice and Bob are using the same basis, right? So they're supposed to be able to generate this information that can be shared by them. But then Eva is using a different photon, a different basis, right? Eva is using a different basis. So Eva actually will get a random number and then have 50%, well, we'll get a random number and then we'll actually change the state, right? Change the state either to horizontal or vertical. So right now, for Bob, instead of measuring 1, right? Instead of measuring 1 like before, Bob has 50% chance of measuring 0 and then 50% chance of measuring 1, right? Because Eva's result is horizontal or vertical, it's 50% each. And then when you use 45-degree basis to measure horizontal and vertical, you're again 50% chance of getting 0 and 1, right? So at this step, you can see that what Eva does to this bit of information is that it actually changed the result. Because Eva's eavesdropping, it changed the result that Bob can receive, right? It actually changed the result. So for quantum key distribution, what people will actually do is that for the first or in the middle, right? Well, actually no, is that they will randomly pick, okay, certain numbers that they share the same basis. For example, this one, and this one, right? There are 3 of them. What you can do is that you can publicly announce what number you have, right? Alice has this number, Bob also have this number. And then if there's no one eavesdropping, then this number should agree with each other 100%, right? And of course, there's a technical limitation. Usually it's 90 something percent. It's not really 100%. But then if Eva is really doing this eavesdropping, and then this qubit here, this bit here, okay, will only have 50% chance of Bob and Alice share the same piece of information. And if you compare a lot of them, this 50% would be very dominant, right? If Eva, okay, did this wrong basis measurement to 100 of information, okay, then 50% of them, when Bob receive it, will be wrong information compared with Alice information. Okay, so in reality, what people do is that they randomly select some information that they know should be equal to each other, and then they examine, okay, how many of them really equal to each other, and then compare this to your system error, right? So any system is not 100%. So if your system is 98% error, but then when you compare it, you see, 80% of the qubit, 80% of the information is the same, but then there are 20% different. Then you know that Eva is doing the eavesdropping. Okay, and in this way, when that happened, you just abandon this entire key and you abandon this channel and don't use it at all. Right? So this way, okay, this is by following this protocol, what you will be able to do is that you will be able to tell if anyone is doing eavesdropping, okay, and then if somebody does that, then you just don't use that channel, okay? It's the same thing. And you might wonder, okay, but that's a waste of, when we try to explain this to people, people would think, oh, but then you abandon the channel, that's expensive, that's blah, 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 and you cannot use that channel anymore. Let's face this reality. When Eva has access to that channel, and then if she wants to stop you guys sharing, key, she can just cut that fiber, right? It's like if someone has the access to your channel, that channel is done, right? It's like even you don't abandon it. If people want to stop you guys from sharing information, she can just cut it. And this happens a lot in the war zone before, like in the World War I, or sometimes even in World War II, where the wireless communication is not that common, right? You actually bring a telephone line, okay, with you to the battleground, and then sometimes the bomb actually accidentally landed on your telephone line, and then you lose communication, okay, with your commander. And this is the same situation, okay? So people can stop you from sharing information, but then they cannot steal that information from you. So in that sense, it's 100% safe. And then we will actually discuss a little bit more over, okay, is it really entirely, completely safe, okay, by considering some, thought experiment of how Eva can attack, okay, this. And then, and then hopefully, okay, this can convince you that the quantum key distribution is a method that's really 100% safe, okay. And that is all for today, and I will stay a few more minutes to answer questions. Thank you, guys.
Hi, Professor. I have a quick question.
Yeah.
What day is the final exam? Or will it be over a week?
Let me think. So the last class is the Thanksgiving week.
I think it's the 24th or 23rd.
Okay, and then what is the plan of the university? So you guys will travel back, or are you guys going to?
I think we'll be traveling home. I don't think I'll be staying in Charlottesville. So I was trying to plan my schedule to see if there'd be a date or if we would have a couple of days to complete it like we usually do.
Okay, so yeah, I will look into this, but I think what I would do is that I would upload the exam right after the, right before the Christmas, after our last class. And then I think I will give you guys at least a week or even more, depending on, I'll check the system to see when I'm required to upload the score. Okay, so does that sound fair?
That sounds very fair. All right, thank you, Professor.